Hello everyone, so in this video we're going to be talking about how reactions actually occur and how we actually diagram chemical reactions. So the main, in this case, component of how reactions occur is actually can be done using this thing called collision theory, okay? So there are three main components of the collision theory, and that's in order for reaction to occur, particles must collide. They must collide with sufficient energy, and they must also collide with an orientation, with the correct orientation. Okay. So one of the, I'm just going to talk about a factor. How do you actually increase, in this case, make reactions much more likely? One of the ways that you can make reactions more likely is the application of heat. Okay. And why is the application of heat increases chemical reactions? Well, it's because heat affects collision theory. Just think about yourself. So if in a cold day, right, a lot of us would rather like sleep, lay out in front of the television with a blanket and just watch some Netflix and chill. Okay, so at that point, folks, so we are not energized enough to go out and actually do stuff. But in the summer, when it's hotter, we'd like to go to the beach. We like to do some running, do some walking. Okay, so heat, right, in this case, create energy between this molecule. So what happens, folks, is once remember, this molecule or this atom in very, very low temperatures does not move. You increase the heat, what happens is now this molecule or this atom is now going to start moving around. Okay, and because they are moving around, what's happening is it's going to be a higher likelihood for these two atoms to collide. So that's number one. The other thing too, obviously, is if the higher the heat, the more you increase the temperature, what happens then is the kinetic energy of these molecules also increase, which means again that also contributes to number two. So it just does not make the particles collide, it also makes the particle collide with sufficient energy. Okay? Now number three really is not a direct, in this case, there's not really a direct correlation to heat, but there's a roundabout way that you can think about that. What happens, folks, is the frequency of collision increases with more heat. Okay, so even if the orientation is not correct when this two collide, what happens is because of heat, the collision rates, the number of collisions between these two particles becomes greater. And because there are more collisions, there is a higher likelihood for them to collide with the correct orientation. So that is one of the reasons why heating something up, right? Cooking is actually a chemical reaction, increases the rate of or the likelihood for a reaction to occur. So again, particles must collide with sufficient energy and the correct orientation. So heat is a big contributor in order for a chemical reaction to occur. The phase of matter is also a big contributor to the foreign reaction to occur as well. If you have a solid, all right, if you have a solid, solids, as you remember, are held together by strong intermolecular forces, which means to say that they have very, very low kinetic energy, so they don't move, right? So in order for a solid to react with something, the first thing you must have to do is you have to vaporize it into the gaseous form, into the gas. Okay, the reason why the preferred phase of matter for reaction to occur is gas is because in a gaseous form there is a higher kinetic energy, which means to say that there's a sufficient energy when two particles collide in the gas phase. All right, so that's also the reason why the gas. So in terms of reactivity, solids are the least reactive, liquids are in the middle, and then gases are definitely the most reactive. Okay, so that's another way that you can actually increase collisions. The other thing is surface area. Okay, one of the things is if I have a big blob here, this is a very, very small surface area as compared to a small blob. Okay, and the reason why that is why the surface area matter is because of number three, with the correct orientation. What happens is if this is the reactive portion of this blob, right, particles are going to collide with this particle, right? Other particles, and then what happens is the likelihood for them hitting this correct area is going to be less, okay? Whereas here, since this is smaller, the likelihood for the correct collision to occur with the correct orientation is actually higher. So that is, again, surface area also matters in this case, all right? And at the end, we're going to talk about catalysis or enzymatic reactions, okay? So again, 3 ways in order for reaction to occur. And all of these things, folks, is we're going to be talking about activation energies and is related to activation energy. So this is an energy diagram. So this is a carbon reacting with oxygen to give you carbon dioxide. So there's always 2 plateaus. There's a plateau on the left side. There's always a plateau on the right side. The plateau on the left side is always the reactants, okay, as indicated here. And the plateau on the right side is always going to be the products, okay? As you can see, this is the actual chemical equation that's written here. Now, no reaction is going to occur without an input of energy. And that input of energy, folks, is you're trying to solve, in this case, you're trying to do the 3 things that we talk about in collision theory. You're trying to make them collide, you're trying to make them collide with sufficient energy, and you're trying to make them collide in the correct orientation. Those 3 things require energy. Okay, carbon, folks, is a solid at room temperature, right? So we all know that the first thing we need to do with, in this case, a solid carbon, is we need to vaporize it first to the gaseous phase in order for it to collide with oxygen gas. That requires energy. So there has to always to be an input of energy. And the input of energy in order for this reaction to occur is called the activation energy. And this activation energy, folks, is all about collision theory. Okay, it's always about the 3 things that we talked about previously. Okay, but once the collisions start to occur with the correct orientation with sufficient energy, the reaction proceeds, and what happens at the end is you actually have the products. Okay, now there are 2 types of reactions. You could have an exothermic reaction or endothermic or endergonic reaction, or you can have an exothermic or an exergonic reaction. And what that is, folks, is just telling you whether, in this case, we're going to be talking more about heat rather than energy based on Gibbs. Is there actually heat that is produced, or is there actually heat being lost? Okay, so in this case, heat is actually being lost to the system. Okay, so if you touch this container, if we know that for a fact that if we burn wood, this is actually just wood or gas, like methane or propane, all right, or octane, the thing that goes into your gas tank, right? We know for a fact when we burn that fuel, we actually have lots and lots of heat released to the environment. Okay, and this is actually why this is a downward. So if there's heat released, you're gonna have a downward staircase. If you have heat being lost, the actual, in this case, reaction getting cooler, you're gonna have an upward reaction like so, which is the opposite of this. Okay, so just remember 2 ways that you can do this. You can actually have losing heat to the environment or gaining heat from the environment. Okay, FYI. You can, if you look at this one, you can actually write this as reverse. So you can actually flip this reaction. You can have CO2 yields carbon plus O2. So it could be the backwards reaction for this one. And as you can see, folks, if that's the case, right, if you're going to go backwards, you're going to be gaining heat, right? You need to gain heat from the environment in this case, all right? So again, 2 types of energy diagrams. If you actually, in this case, becomes colder or you gain heat from the environment, you actually have an upward. So this means to say that you're going to have a, just to give you a clue, you're going to have a positive Q. For our purposes, I'm going to generalize, and here you're going to have a negative Q. All right, getting cooler, the reaction is getting cooler. So if you touch the container of this reaction, it's getting cooler, and here it's getting hotter or warmer. Okay, so that's the main key. So we're going to be talking about heat more in terms of this class. All right, now how do you get positive Q or negative Q? Well, the way you do this, folks, is you actually use this, in this case, the formula Q equals ms delta T, which is actually in your exam reference sheet. Okay, and M stands for mass, S stands for specific heat, and delta T means change in temperature. Okay, now here is the deal. Most of the equations out there in the website will tell you that it's final minus the initial. I'm going to tell you right now it's going to be initial minus final. And the reason why is this is the only way that you're going to get a positive Q or a negative Q. So in this example, what happens is you take the mass of water times the specific of water times the change in temperature, initial minus final, you get a negative delta Q. This negative number means to say that it's a downward staircase. Okay, if this was a positive, it would be the opposite. It would be an upward staircase. All right, and this bump, this input of energy required to actually start this reaction is actually given to you in this case. I have to tell you that, and it's 100 calories. And if you can see, again, the difference here is 100 calories, and this here, the span of distance between this reactants and products is actually negative 1500 calories, meaning to say that this is an exothermic reaction. Okay, so again, you can find whether the reaction is exothermic or endothermic by doing math, or I'm gonna give you a number. If it's a negative number, it's gonna be downward staircase. If it's a positive number, it's gonna be an upward staircase. Okay, now one of the things is correct orientation, sufficient heat, collision is we're going to talk about catalysis here in this case. So catalysis, folks, so again, we need to have an input of energy, right? So the greater the input of energy that we need to make collisions likely, to make particles collide with sufficient energy and with the correct orientation, the longer it takes for this reaction to occur. Okay? However, if we lower the activation energy, this reaction is going to proceed faster. And this comes from this term called catalysis. And catalysis comes from catalysts, okay? What are catalysts? Catalysts, folks, are things that speeds up chemical reaction. And how do they do this? Well, I'm going to give you the classical example of catalysis here. If we have two particles very, very far away from each other. As you guys can see, the distance between these two are very, very far. Are they going to collide? No, their distance is quite far apart from each other. Okay. Now let's say that there's very, very low heat. So that means to say that they will not have sufficient energy, which means to say that they will not collide with the correct orientation as well. What catalysts do, folks, is all they do is they bring these two particles closer together. So it's all about distance, right? So if I'm a catalyst, let's say I'm a catalyst here, okay? I'm just gonna create like a catalyst of some sort here. And what happens, folks, is I'm gonna plug them. What the catalysts do is they bring these two particles closer together. So now they're going to collide because they're closer together, right? Furthermore, they're gonna so that the reason why they're closer together, now they might not have sufficient energy, for instance, but however, since they're closer together, the likelihood for them reacting is higher, and that is why you actually lowered the activation energy. So the main key for knowing whether a reaction is being catalyzed or not is looking at the activation energy. So let's say if the first reaction looks like this, and then I give you something with a smaller hump, the lower the hump, the more likely that there's a catalyst or an enzyme involved. In biological system, catalysts are actually called enzymes. Okay, so in living systems, the catalysts are actually enzymes. FYI, if you've ever heard of a catalytic converter, that is actually what it does. What it does is it actually, in this case, prevents the creation of harmful nitrous oxide components that actually are, in this case, greenhouse gases. So what you do is if you have a catalytic converter, you get more production of nitrogen gas and oxygen gas rather than having nitrous oxide substances or particles. Okay, so again, all of this is about collision energy.